function, a variable that's declared outside of any function, and also is not an element or data member of a heap dynamically allocated array, right? So a heap, if you create an array using new, then that would be a heap dynamically allocated array, right? If you create an object using new, that would be a heap dynamically allocated object. So if you have a variable that is not local to a function and also not an element or data member of a heap dynamically allocated array or object, then static allocation will be used for that variable, right? So those variables are given statically allocated memory allocations. And also, if you have a local variable of a function that is declared static, right? Or if you have a variable of a class that's a static variable, then the variable will receive a statically allocated memory location. And characters of string literals in C++ are stored in statically allocated memory locations. Now let's look at what happens in TinyJ. Now in TinyJ, if you have a variable that's not local to a function, you have to declare it static. That's because that's if you look at the definition of TinyJ, it doesn't give you a choice. Okay, so you can either have variables declared inside main or inside some other method, or you can have variables declared in within a data field declaration. But a data field declaration always begins with static. So therefore, any variable that's declared outside of a method must be declared static. Conversely, if you have a variable that's declared inside a method, you can't declare it static, right? It's just not allowed because nowhere else, you see. So if you look at statement, right? So variable declaration is one kind of statement, but VARDEC doesn't have a static here, right? So the only way you can use static is here, right? Where static before the VARDEC, and that only appears in data field peg. So static, a variable is static, that is declared with the word static if and only if the variable is declared outside of any method. That's in TinyJ. Okay? So TinyJ, static variables are exactly the variables that are declared that are not local to a function. And so so just as in C++, those variables are given statically allocated locations. Also, TinyJ string literals are stored in statically allocated locations. Right. So TinyJ is analogous to C++. You can't have elements of arrays that are declared as static. Now you have to be a little careful here, right? So if I write static int x, I am not declaring an array here, right? I'm only declaring a reference to an array, right? So you've got to be careful because as in Java, this is not creating any array. Now later on, I can say x equals new int 100. Now when you evaluate this expression, that's when an array is created. But there is a distinction between the array and the x. X stores a pointer to the array. So this is x's location. X stores a pointer to this array. So the array is here, right? So this would be x of 0, right? And then x of 1. And here's the last element of the array. Sorry. The last element of the array, which the 100th element of the array, right? Like that. So x is here. So this thing is statically allocated. Statically allocated. Why? Because of the word static, right? But the array on this is heap dynamically allocated. So I'm just I'm making sure that people understand. So this part, that part is heap dynamically allocated, right? X is statically allocated, right? So there's a distinction between X, which holds the reference, and the array itself. So x0 is heap dynamically allocated, right? So x0 is heap dynamically allocated. Right. X0 heap dynamically allocated. X is statically allocated. Because X is here. X0 is here in the heap. So this is something that has confused some students in past semesters. So I just wanted to be quite clear about this right now. I'll probably say something about that again at a later time. All right. When are statically allocated memory locations allocated? Answer: they are allocated before program execution begins. So let's give a concrete example. So if we look at 12.sol, remember that was what happened when we translated the CS316x1.java program, 1.sol rather. So if we look at this, let's look at generated code. So the program is executed by executing these instructions. And what I'm saying is static allocation happens before any of these instructions are executed, right? So when static allocation happens, nothing has been executed yet. So static allocation happens before execution of program. And when are statically allocated memory locations deallocated? And the answer to that is never. The allocated locations remain allocated for their original purposes until the program terminates. So they're allocated permanently. Okay, so you start executing, then all the statically allocated locations remain allocated until you get to this stop. Stop says we've reached the end of the program, and so control will then be returned to the operating system. Notice, by the way, that the machine starts executing like this, but when it gets to a call stat method, then it calls a method, in this case 18. So you would jump around this stop and you would actually start executing at 18, right? And so you would execute all this stuff, and then there's a recursive call at one point, right? This is a recursive solution to the Tower of Hanoi problem. So here you have a recursive call, and this whole method actually doesn't end until here. But I'm mentioning this because the thing you need to remember is that the stop instruction is when you stop, when the program terminates. Okay, so there's this call. When this call returns, then NOP is executed, which actually does nothing, and then stop is executed, and then the program terminates. However, this call makes a recursive call before it returns. What actually happens is that it will make a recursive call. The recursive call will return to the caller. So it's not. But the important thing is this is the point where program execution ends. Right? The stop instruction causes the execution to end, and while instructions are being executed, the statically allocated locations remain allocated. Right? So statically allocated locations are never deallocated. The locations remain allocated until the program terminates. So in the case of TinyJ, that means until the stop instruction is executed. Now, since TinyJ is a subset of Java, I think it's important to mention that Java has a completely different allocation strategy. So Java and also Lisp are languages that do not use static allocation at all. All right. So in these languages, memory for all variables and stored data is allocated during program execution. In other words, dynamically. Dynamically means during execution. So in the case of TinyJ, things that happen dynamically are happening during execution of these things. Right. All right. So if you have a static variable of a class in Java, then those variables will have space allocated to them when the class is actually loaded into the Java virtual machine. And when will the class be loaded? Well, actually, the time when classes are loaded is up to the Java virtual machine, but a typical Java virtual machine loads classes on demand. That is, it loads a class when the class is actually used. So if the class is never actually used, then that class is never loaded, and the static variables of that class will, in fact, never have space allocated to them. So a typical Java virtual machine loads loads a class when the class is used for the first time during code execution, right? During execution of the bytecodes. In other words, it will load the class the first time one of the following happens. The first time you create an instance of the class, or you call a static method of the class, or you access a static variable of the class. Right? So until one of those things happens, a typical Java virtual machine won't load the class, and so the static variables of the class won't have any memory locations. And as far as string literals are concerned, so I said in TinyJ, as in C++, they're given statically allocated locations. This is not true in Java. String literals in Java are strings, which are objects, and like all objects in Java programs, they are allocated on the heap. Right? Another interesting thing about Java string literals is that they are memory unique. What actually happens is a Java string literal is created in heap memory the first time the Java virtual machine loads a class in which that particular string literal occurs. Actually, this isn't always true. There are unusual cases where an equal string has already been cached in the string literal pool, but that's certainly uncommon. And after a particular string literal has been created, the string is actually cached in a pool of cached strings that is maintained by the Java virtual machine. So if that same string is needed again, then it won't be created again. So if you've got a certain string that's used in 50 different places in your Java program, as long as it's a string literal, right? We're talking about string literals here. Then only one copy of that string is going to be created, because the first time that string is created, it is cached, and the next time that same copy of the string will be used. Right? So it doesn't matter how many times a particular string literal is used in Java. Only one copy of that string object is going to be created. But this is the Java. This is not true of TinyJ. And remember, in Java, the string literals are stored in the heap, right? Whereas in TinyJ, they are stored in statically allocated locations. So I wanted to emphasize this, because TinyJ is a subset of Java, as I told you before, but that doesn't mean that what I said about static allocation of space for static variables in TinyJ also applies to Java, right? I want to make sure people are aware of this difference. All right, so now I want to take a look at the TinyJ virtual machine's memory. The TinyJ virtual machine's memory consists of the expression evaluation stack, data memory, code memory, and some registers. Now, data memory, that's the second part here, is itself subdivided into three parts. Right? The statically allocated part of data memory, right, used for static allocation. The dynamically allocated part of data memory, which is used for stack dynamic allocation. So in addition to static allocation, we also have stack dynamic allocation. And then there's the heap area of data memory used for heap dynamic allocation. Right? I showed you one example of this. Right? I said that the array is allocated in the heap. Now, what about code memory? Code memory is here. Code memory stores TinyJ virtual machine instructions for execution. So when these instructions are being executed, they are actually in code memory. All right. So to execute an instruction, that instruction is fetched from code memory into an instruction register, actually, and then the instruction is executed. So instructions are stored in code memory, executed. And contents of code memory can't change during execution of a TinyJ program. Code memory and data memory have separate address spaces, by which I mean, say, address 4 in code memory has no relationship with address 4 in data memory. Just like 4th Street in Manhattan is unrelated to 4th Street in Philadelphia, because Manhattan and Philadelphia have separate address spaces. Okay. Now, I will be saying something about the registers when we get to TinyJ assignment 3. I might say a word or two about registers even before then. But for the most part, you don't have to worry about the registers until you have to do TinyJ assignment 3. Let me show you a picture just to help you remember what I just said. So the TinyJ virtual machine's memory. There's the statically allocated part of data memory. There's a stack dynamically allocated part of data memory. There's also the heap dynamically allocated part of data memory called the heap. That's going to be shown here, but on these slides, I'm also showing the expression evaluation stack here. So there's the expression evaluation stack, and now there's the heap. Right, the heap is here. The heap dynamically allocated part of data memory is also called the heap. And then we have this code memory, and the instructions that are going to be executed are stored here. Right, so to execute instructions, you fetch them from here. And execute them. Fetch an instruction, execute it. Fetch another instruction, execute it, and so on. All right, so get back. Now, static. Well, we're going to deal with the static case first. Static memory allocation rules used by the TinyJ compiler, and the rule for variables is extremely simple. The nth static variable, regardless of whether it's an int or an array reference variable, is given the data memory location whose address is n-1. So, for example, the 7th static variable gets address 6. Now, this rule does not apply to scanner variables. Scanner variables are not real variables in TinyJ. Let me click on this. There's a paragraph here that says something about scanner variables. They're not real variables. They're fictitious variables. Basically, if you've got a scanner variable x, you can only use it in an expression of the form x.nextInt. And when you execute this, it just reads an integer from the keyboard, right, or from system.in, which is usually the keyboard, and returns its value. So the x is completely irrelevant, right? You don't need the x. You're just reading an integer from system.in and returning its value. So why have the x there at all? You know, why isn't this just x? And the answer is very simple, because we want TinyJ to be a subset of Java. Because I thought it would be much easier for people to test TinyJ programs if they could just compile them using a Java compiler. Right? And so the reason there is an x here at all is so that the statement will still be legal in Java. Okay? So the scanner variable x in x.nextInt is there only because we want TinyJ to be a subset of Java. So TinyJ programs will be compilable by a Java compiler. So the thing to remember is, So the thing to remember is that scanner variables are fictitious variables. String literals, right? Well, the kth string literal character is placed into data memory at the address m plus k, where m is the last address allocated to a static variable. So if addresses 0, 1, 2, and 3 are allocated to static variables, address 4 will be the first string literal character is placed. Okay. All right, so let's look at a concrete example. So here is a program. So which memory locations are statically allocated for this TinyJ program? And what variables and data would those locations be allocated for? All right, so let me just remind you, we're going to use this very simple-minded rule. What was this rule? Here we are. We're going to use this rule. Nth static variable is given the address n-1, right? Okay. So scanner variables don't count, as I just mentioned, and that's not actually a variable. So x is given address 0, y is given address 1, and z is given address 2. Right, let's look at this picture. Right, so x is given this address, y is given this address in data memory, and z is given this address. Now, all of these locations are within this part, the statically allocated part of data memory. So to execute y equals 10, you need to execute instructions that will cause the value 10 to be placed in location 1 here, because y's location is 1. All right. Now, going back to what I said here, the kth string literal character is placed at address m plus k, where m is the last address allocated to a static variable. Right? You see that after this, you have the places where enter x and enf will be stored, right? So first enter x, all right? So e gets put in location 3, n into 4, and so on. And there's a space here, which is a perfectly good character. So that goes into the location 11, location with address 11. And then after that, you have the characters of this string, like that. Strings in TinyJ are not null terminated, right? So this is TinyJ is different from C++ in this regard, right? So C and C++, you will have learned that the strings are terminated with a null NUL character, right, with character code 0, but that's not true of TinyJ. Okay. Now, the only reason why you have a space here and a space here is just because this string literal ended with a space. If I put this double quote immediately after the colon, then you would not have this location 8 storing a space, right? In that case, this X here, I'm sorry, not location 8, I mean location 11. In that case, location 11 would store this I instead, right? Because you would store the first character of this string. So the fact that location 11 contains a space is just because I happen to have a space in this string, literal. All right, so that's how static allocation works for this particular program. Now, one question you might be asking is, aren't we wasting a little bit of space because an int needs 4 bytes, but a character certainly doesn't. Even a Unicode character only needs 2 bytes. And so the answer to that is yes, we are wasting a little bit of space for the sake of simplicity. Because what I'm doing here is giving each thing one location. And so in the case of characters, that's wasting a little bit of space, but that simplifies the job of the compiler and it simplifies the virtual machine a bit. So those of you who think that I'm wasting a bit of space, yes, I am. And the reward is the compiler and the virtual machine are slightly simplified. All right, so 18 locations are allocated as shown here. Now we're going to talk about stack dynamic allocation. Back here. So what is stack dynamic allocation? So what does it mean? Well, it means the allocation from an area of memory called a stack, and the locations are deallocated in last in, first out, last allocated, first deallocated order. Now, question number 1. What are stack dynamic deallocated locations used for? They are used for formal parameters and other local variables of functions and methods, okay? Which is all methods. And also, when you're evaluating an expression, the values of its operand sub-expressions will be stored in stack dynamically allocated locations, as will the value of the expression itself. So if you look at this big expression, so here we have 2 operand sub-expressions, and these 2 x and y are sub-expressions of the first sub-expression, and z and w are sub-expressions of the second sub-expression. So sub-expression values are placed in stack dynamically allocated locations, as is the value of the expression itself. Now notice I actually said conceptually, because the compiler or interpreter writer is allowed to do things actually differently under the hood, so to speak, provided that from a programmer's perspective, the program behaves as though these 2 things are true. So for example, it's quite common for a compiler writer to generate code that actually places some values in processor registers. So if you're compiling for a CPU that is in registers, then instead of placing formal parameters into stack dynamically allocated memory locations, you can place many formal parameters inside registers where you can access them more quickly. Okay. Again, if you're evaluating an expression and a certain sub-expression is a variable x, then since that variable already has a location, then the compiler writer may generate code that doesn't actually even allocate a new location for that sub-expression, because that sub-expression is a variable which already has a location. Or if a particular sub-expression is a constant, like 5, then again, it may not be necessary to allocate a location for 5, because the CPU may have an instruction that allows you to use 5 without having 5 stored in a location. Right? So what actually happens under the hood may not be exactly like this. However, from a programmer's perspective, the program behaves as though stack dynamic allocation happens in those cases. And in the TinyJ virtual machine, this is actually what happens, not just conceptually. Okay, so in the TinyJ virtual machine, this is really what happens. But just bear in mind that for other languages, the compiler writer or interpreter writer has freedom to get the most efficient, produce the most efficient code, and sometimes that means not actually, so it's making things behave slightly differently in reality. The TinyJ virtual machine uses 2 different stacks for A and B. The stack for A is the TinyJ virtual machine's data memory. and the stack for B is the expression evaluation stack. However, many virtual machines use just one stack. So the Java virtual machine would use the same stack for formal parameters and local variables as it uses for expression evaluation. Right? So that using one stack is very common. The TinyJ virtual machine actually uses two different stacks, however. When are stack dynamically allocated locations allocated? They are allocated for purpose A, right, for formal parameters and other local variables when the method is called, right? So that means when you execute a call stack method and when you execute the init stack frame, that's when space is allocated for the formal parameters and local variables of the method that is being called. For purpose B, there's a choice. You can either allocate the space when the function or method that contains the expression is called, or you can allocate the space while the expression is being evaluated. So both of those are possible. And for TinyJ, the second option is what happens. And that's true for in Java as well. So space is allocated for sub-expression values while the expression is being evaluated. When are stack dynamically allocated locations deallocated? Well, if the locations are allocated when a function or method is called, they're deallocated when the function or method call returns control to its caller, right? That means in this case, when you execute return, then the locations that are allocated when the method is called will then be deallocated. But a location that's allocated while an expression is evaluated is deallocated after the value that it stores has been used. And now let's take a look at the actual rules. So the rule is very simple. Right, let's start here. So each time you call a method, a block of memory locations called the stack frame is allocated. And this block of memory locations is deallocated when the method returns control to its caller. And each formal parameter of the method and each local variable declared at the method's body will be given one location in that stack frame. And we refer to stack frame locations using offsets. So for example, if in a certain location the address of offset 0 is 73, then the address of the location at offset 5 is 73 plus 5, which is 78. Now when the compiler sees a declaration of a variable, of a local variable, right? It will give, by which I mean a local variable declared in the body, right? I'm not including formal parameters here. The local variable is given the first stack frame offset with that is at least 1, which is not already allocated to another local variable that is still in scope. Okay, let's look at an example. So A gets 1, B gets 2, C gets 3, D gets 4, E gets 5. What does F get? F gets 4. Why? Because D and E are not in scope anymore. So A got 1, B got 2, C got 3, so F gets 4. G gets 5, H gets 6. Now what does this I get? Well, D, E, F, G, and H are not in scope anymore. So A got 1, B got 2, C got 3, so I gets 4. Right? So the answer is given here. Right? So make sure you go over this example again after class and you arrive at the answers that I just gave you. And what about formal parameters? The rule is very simple. The last formal parameter gets offset -2. The second last gets -3, and so on. So R here gets offset -2. Q gets offset -3. And P gets offset -4. Right? The last gets -2. Second last is -3, and so on. So let's finish with a quick example. So consider this program. So in a stack frame of this function, how would the offsets be allocated? All right. So this is a stack frame of any call of my func. Now you'll have noticed I didn't say anything about offset 0 and -1. So when we get to assignment 3, I will. So offset 0 and -1 are actually used for the dynamic link and the return address. So you don't have to worry about those right now. All right. So Z gets -2. Right. Y gets -3. And X gets -4. A gets 1, B gets 2, C gets 3, D gets 4. E gets what? Well, C and D are not in scope anymore. So E can get the location C gets, right? So E gets 3 as well. And F can get 4, right? G gets 5. Now what about H? Well, E, F, and G aren't in scope anymore. So H can be put into the place where E was, right? So H gets 3. I gets 4, J gets 5, and K gets 6. So that's how any step, whenever you call the function, a stack frame is allocated and used this way. And let's take a look at how stack frames are allocated and deallocated. So suppose we have a situation where when you execute a program, when you run a program, main is called. So a stack frame for main is allocated, right? Main calls F, then a stack frame for F is allocated. F calls G, stack frame for G is allocated. G calls H, H's stack frame is allocated. H calls F, right? F stack frame is allocated. Now we have 2 stack frames of F because of recursion. F returns control to H, right? Then we have this. H returns control to G, so we have this situation now, and G calls F. All right, so I think we'll stop there for today. So what I've just done is basically this example, right? And so you should verify that what you see here is exactly what I just showed you here, right? So this is just illustrating. So in some past semesters, I just asked people to read this, which I think is fine, but I thought that showing you a picture would be more helpful. So that's what I did. Okay, but you should verify that what I've just shown you here, right, is exactly consistent with what is described in words here. All right, so let's. Oh, we're actually out of time. So let's stop there. So does anyone have any questions right now? Let me turn the recording off and